bonds where the sharing isn't equal. Now, how do we know what atoms will have a big, strong pull on electrons and what atoms will have a relatively weak pull on electrons? The electronegativity, because electronegativity is a measure of that. Now, we can look, that number is on the periodic table for each atom. If you look here, this periodic table has the electronegativities right up here. All right, it shows them to us. But as a general rule of thumb, what has a stronger pull on electrons? Metals or nonmetals? Nonmetals. Nonmetals, because they're close to having a full shell, as a rule of thumb, are trying to get more electrons. Even when they share, they're greedier. They're pulling on them. They tend to have strong electronegativities. Metals, because they have few electrons, tend to have very weak electronegativities. And even more to the point, the further right on the table we go, the stronger the electronegativity, right? So we would expect that fluorine would be more electronegative than oxygen. And we'd expect that oxygen would be more electronegative than carbon, which it is. Does that make sense? Questions about that? I'm not too worried about the periodic trend for this class because you can actually just look at the periodic table and look at the number. For this note, I've even put the periodic table right on the page for you. All right, so we've got it right there. So today we want to go a step further. You know how to look at two atoms and compare their electronegativities. And does anyone remember the rough range? If the difference in electronegativity, and by the way, how do we show difference in science? How symbolically do we show that? Delta, good. Greek letter delta. So if the difference in electronegativity, is everyone comfortable with En as electronegativity? Does anyone want me to write it out? I will. So this is kind of an arbitrary number, and some books say 0.3. I've seen some that say 0.4, some say 0.5. There's kind of an understanding that this is just a guideline. But as a rule of thumb, if the difference in electronegativity between two atoms is greater than 0.5, we say the bond will be polar. By the way, if it gets big enough, eventually it'll actually be ionic. It'll actually transfer. But we're talking about covalent bonds here. So that's our rule of thumb. With that in mind, let's take a look at carbon disulfide, CS2. So if I want to draw a Lewis structure of this, what's the first thing I do when I draw a Lewis structure? Sure, which in this case will be carbon, and it'll be surrounded by sulfur. But of course, before I do that, what do I really want to do first so I know what I'm doing with this? Count the electrons. Good. How many do I get from carbon? 4. How many do I get from each sulfur? 6. And there's 2 of them. So my total is 16. Good. Okay. Once I've drawn the middle atom and the surroundings and drawn single bonds between them, what should I be doing now? I ask you. What do I do now? Just run a Lewis structure. Done lots of these this week. Fill up the octets. Do I fill up the octet on carbon like this? No, we save that for later, right? Because we don't want to put too many electrons in. By the way, there's nothing magical about this particular rule for doing it. It's just one way. Right? There's nothing magical about filling the surrounding one first. It's just a way of making sure you don't put too many electrons in. What do I do now? Count again. So I've got, what, 2, 4, 6, 8, and both sides are identical, as Caleb would no doubt tell me, and he'd chastise me if I counted the other side as well. That's a total of 16. So do I have enough electrons? Yeah. Can I add more electrons? No, this is all I've got. Problem being what? Carbon needs 2 more bonds. So what should I do? What do you think? 2 double bonds? Great. So I'm going to take these electrons away, and we're going to give double bonds like that. Yeah.
Which still work if you give one of them a triple bond? Or
It, in theory, would work, but this is the preferred structure. And if you do the reach ahead lessons, you'll know why. Little plug. Okay, so there we go. That's carbon disulfide. Now, in the question of whether this bond would be polar or not, we compare electronegativities. So if we look at carbon, what is its electronegativity? 2.55. If we look at sulfur, what's its electronegativity? 2.58. What, therefore, is the difference in electronegativity between these two things? It'd be 2.58. How do you find a difference between two numbers? You subtract 2.58 minus 2.55, and that is a difference of 0.03. Is that a polar bond? So this would be a non-polar bond. Now, here's the point. This bond between carbon and sulfur is non-polar, right? What about this bond between carbon and sulfur? Also non-polar, right? They're the same bond. Excuse me. So, if both bonds are non-polar, what about the molecule on the whole? Yeah, if there's no polar bonds, the molecule can't be polar, right? Does that make sense? So, if the bond is nonpolar, and if all the bonds are nonpolar, the electrons inside the atom have to be shared roughly equally, and if the bonds aren't polar, the molecule on the whole can't be polar. Does that make sense? So this whole lesson is going to be about figuring out if a molecule is polar. And the first thing you have to check is if the bonds inside that molecule are polar. Does that make sense? And in this case, they would have incredibly low polarity, 0.03. On the other hand, if the bond is polar, the molecule can be polar. So let's look here. This is a nice, easy one. A Lewis structure between hydrogen and chlorine. Well, that's easy. Hydrogen, chlorine. How many electrons do we have to work with? Hydrogen gives us... How many electrons in hydrogen's valence? 1. How many in chlorine's valence? 7 for a total of 8. Okay, what do I do next? Fill up the octet. Now, does hydrogen get a full octet? No, it can't, right? How many electrons do I have? 8. Okay, so there we go. We have a good structure. Now, what's hydrogen's electronegativity? Sorry, I'm not going to use red. Very pointedly. So hydrogen has an electronegativity of 2.2. And chlorine? 3.16. So what's the difference in electronegativity here? Not 0.96? Okay. That's okay. I'm still not convinced you're wrong, but whatever. That's what I'm going with. So the difference is 0.96. Now, is that polar? Yeah, because we said it's polar if it's what? 0.5 or greater. And this is greater. It's 0.96. Good. Now, which one has the stronger pull-on electrons? Chlorine. Okay. And we show this on a Lewis structure like this. We draw a dipole. All right, and this is referred to as a dipole. The arrow points towards what? Right? Yeah, it points towards where the negative is. In fact, we would say that this side of the electron, this side of the bond has more, the electrons more often. That's where the arrow points. The arrow points where the electrons spend more time. So this side of this molecule will take on a slightly negative charge. And this side of the molecule then would take on a slightly, very good, slightly positive charge. And this is what we call a dipole. There we are. There's a great little piece of software that you can all use. It's a great way to check your work, by the way, called Mol Viewer. It's incredible. This is like the kind of software that used to be quite expensive, and now you can just go online and get it for free. Can everyone see that? It's just a 3D space-filling model of what we just built. Hydrogen and chlorine bound to one another. And the cool thing is I can actually go in here and I can look for what it calls bond dipoles. I can click that and it'll actually show. And it's really easy to see on my screen. I wonder if you can see it okay from there. But can you see how they've put like kind of a little tick on the arrow there, and there's the point of it? And so this is showing that the dipole points in the direction of the chlorine. Jade, do you mind actually getting this light? This one here? And do you not have this note, Jade? Okay, I'll bring it to you. You get the light, I'll get you the note. So again, can everybody see that? So it shows the dipole, and the dipole points towards the negative side of the molecule. It points to where the electrons naturally want to spend their time. Yeah? Hydrogen and what? Yep. So that arrow, the tip points to the negative charge. And again, we say that this molecule has a dipole. By the way, the arrow isn't the dipole. The arrow is the symbol for a dipole. A dipole has physical meaning. A dipole is a partial charge in an atom. All right? Dipole, by the way, is a really stupid word. But it just describes the fact that the molecule has two poles. One side of it has a slight positive charge. One side of it has a slight negative charge. Yeah, no, it's true. It's not a terrible name, but it's not great. Does anyone have any questions about that? So all we had to do to know which way the dipole went was look at the difference in electronegativity. Caleb told us there is a dipole because that difference in electronegativity was numbers. Specifically, what kind of numbers? Well, small, but bigger than 0.5. And then how do we know which direction to draw the arrow? Yeah, and how do we know which end that'll be? That's right, the more electronegative one. You're going to see that rainbow pen from time to time. I'm a fan. Okay, so what I want to do, though, is look at the case of carbon dioxide. Let's draw a Lewis structure of carbon dioxide. Now, the formula for carbon dioxide is CO2. Okay, so let's count. Carbon gives me how many electrons in its valence? 4. Oxygen, 6. And of course, there's 2 of them for a total of 16. Okay. How am I gonna draw this thing? Yep. Yep. Very nice. Okay, so what atom goes in the middle? carbon. Oxygens go around it. Next step, as always, is to do what? Fill the octets. When I do that, what should I do next? Count, and I get 2, 4, 6, 8, 10, 12, 14, 16. So can I add more electrons to carbon? No, so what do I have to do? Very good. Is that starting to feel just like straightforward and like second nature? I hope so. I put a boatload of questions for practice on today's note. So if it's not feeling like regular easy yet, do all the homework. It will. Okay, now let's look at the difference in electronegativity. What is carbon's electronegativity? Great. What's oxygen's? Yeah. Very good. So the difference in electronegativity would be 3.44 minus 2.55. 9, 8, and 0. So 0.89. Assuming I can still do arithmetic. That work? So is that bond polar? Okay, so that's a polar bond. Okay, so let's go draw those in. If we look here, from carbon to oxygen, which way should the arrow point? Oh, actually, before we do that, really quickly, what kind of bond are these? This bond is sigma. This bond is pi. This bond is pi. Hey, what's the hybridization here for carbon? Carbon is sp hybridized. How'd you know that? Just quick glance at that. How do we know it's sp? Yeah, how many pi bonds does it have? 2. So from sp3, 1 pi bond would mean sp2. 2 pi bonds means sp. Hey, if this is sp, what's the shape of this thing? CO2 is linear. This makes a perfect straight line. If we wanted to put the bond angle, it'd be 180 degrees, right? Okay, with that in mind, and if you wrote that, don't worry about erasing it. Doesn't matter. I just want to be really clear up here. With that in mind, carbon, oxygen, which way is the arrow point for this polar bond? Well, it should point towards the one where the electrons are spending more time, right? Let's take a look. Which one wants electrons more? Oxygen. Good. Hello, computer. There we are. Oh, you're finicky today. So we're going to point towards oxygen. Now that takes care of that bond. What about the other bond? So like this? The other way. Okay. So it's going to be the same thing, but of course it's pointing in the opposite direction because the oxygen's on the opposite direction. Now, what do you notice about those two dipoles? They cancel each other out because they're the same size, right? They both are a dipole of 0.89, but one is going to the left and the other one is going exactly to the right, and they're 180 degrees away from each other. Now, if you have taken physics and you know about vectors, or if you take calculus and you know about vectors, you can actually do the math to see these. But I picked a really easy example because they are the exact same size and they're going in exactly opposite directions. That makes sense? So these two dipoles cancel each other out, which means that there is, I'm going to do it in purple, no overall dipole. Which means that we have polar bonds, but the molecule is nonpolar. Let's take a look at that again. The bonds are polar. We have electrons spending more time over here, which gives us slight negative, and we have electrons spending more time over here, which gives us slight negative. But keep in mind, that this end of the molecule has a slight positive because of this dipole, and this end of the molecule has a slight positive because of that dipole. And so on net, there is no dipole. They cancel each other out. And you can see this going back to the online molecule viewer. So if we take a look here, I can plug CO2 into this. Oh, there's CO2. You can see it. Look at all of its complex 3D glory. And if I go here to Jmol, first I can show the bond dipoles. And it's going to show exactly what we expect, right? One dipole pointing towards this oxygen, the other dipole pointing towards that oxygen. Does that make sense? But now if I go to Jmol and I click overall dipole, it should add an arrow for the total dipole. But watch. Nothing. That makes sense? Compare that to water. We know that water is polar, right? That's the first example we always teach as polar. If we look at water, when I add the bond dipoles, one of them goes from this hydrogen to that oxygen. The other one goes from that hydrogen to that oxygen. They cross like this. When we put those together, what are we going to get? A dipole in the middle, right? The left movement will cancel out the right movement, but they both move towards the top, right? And so here, if I go overall dipole, we get the charge there. Does that make sense? So in the case of water, they do not cancel each other out. We have two dipoles, but because they move both forward, we get overall a forward dipole. Does that make sense? But in the case of CO2, yes, we have dipoles in the individual bonds, but when I go to give it an overall dipole, nothing to be had because there isn't one because they cancel each other out. Does that make sense? Does seeing it visually like that kind of help? I know it helps me. I'm going to use my banana to hold my power cord in space. Now, I placed one of these with a different atom. Well, that was awkward. What happened?
You killed it.
I did kill it, but I don't know why. Oh, okay, we're back. If I replaced one of these with a different atom or with a lone pair of electrons, it would work. Does that make sense? So if I had, oh, I don't know. If I had carbon to oxygen here, oh. But then on the other side, instead of oxygen, I put sulfur. Now we have a different animal. Does that make sense? Because now the carbon-oxygen bond, we know about its dipole, right? We just calculated it, 0.89. Which way does the dipole go from carbon to oxygen? Towards oxygen. But what about carbon and sulfur? What's the difference in electronegativity there? It's on the diagram right above. Almost like I carefully planned this lesson out. 0.03. Okay, is that polar? So this now has only one dipole. And so if that is the bond dipole, the overall dipole points in this direction. Does that make sense? So if instead of having an oxygen there, we had had sulfur, now this thing would be polar. I was going to say bless you. That doesn't really work, but I sympathize. It's the overall dipole. Does that make sense? You don't even need to necessarily draw that. I'm just showing that because this one bond is polar. Maybe I'll even show it over like the whole molecule. So it just means that this is a dipole. There's nothing else to cause the not to be a dipole, so it stretches along the whole thing. So replacing an oxygen with sulfur, oh, bless you. Thank you. Well, thank you. That's very kind of you. I should probably teach that lesson. That's what I should do, not to you guys. Makes the whole molecule polar. Yep. Sorry?
Does that make it more polar?
No, so CO2, the way they work out is they cancel each other. So it's not polar at all. Even though we have two polar bonds, overall, not polar, because they cancel. Think of it this way. Like in a tug of war, if on one end of the rope you have somebody really strong, right? Then his super strength makes that thing polar. But now if you put that on both sides pulling in opposite directions, in theory, the thing in the middle won't move at all. Does that make sense? So dipoles, it's not enough to have a dipole. The dipoles have to work together, or at least not work against one another. Does that make sense? By the way, every example we've looked at so far has been two-dimensional. Guess what we're going to look at next? That's right. We're going to look at dipoles in 3 dimensions. Yeah. Yeah, of course. Also. Yeah, oh, of course. Yes. You could even say, like, because there's only one dipole. Right, so it can't cancel. And you see now why shape matters. Because if this were, if CO2 were bent, you'd get a dipole. But because CO2 is linear, you don't get a dipole. Does that make sense? So the 3D shape of molecules matters. All right, am I good to move on? I don't want to rush anybody. I got nothing but time. I mean, that's not true, but it's the kind of thing you say to be encouraging. Okay, let's try one out in 3 dimensions. Let's make carbon tetrachloride. So talk to me about carbon. How many electrons in its valence? Cool. Talk to me about chlorine. How many in its? 7. And of course, there's 4 of them. Sometimes 4 is. Great. So my total number of electrons is 32. All right, this is a big one. How do we draw it? We put carbon in the middle, and of course around it we put chlorine, right? Okay, what do I do next? We'll talk. We'll talk. You can't yet because you don't know what shape it is yet. So what next? Yep, very good. And we have 32. So that's a good structure. Okay, let's talk about these bonds. What kind of bonds are they? Let's say carbon has what? How many? So it's got 4 sigma bonds. How many pi bonds? Oh, already written it. How many lone pairs? Okay. So what is carbon's hybridization state? What is it? Very good. Very good. What will all of those bond angles be? They'll be 109.5 degrees. What do we call that shape? Very good. And if we wanted to draw it really accurately, we'd actually draw it like this, right? We'd say chlorine's up here, chlorine's down there, and then this chlorine like comes out at us. It's coming to get us, and that chlorine is like running away from us. I'll even make this one like really big. Now, let's talk about the bond between carbon and chlorine. Is it polar? What's the difference in electronegativity? Anybody? What's carbon's? Great. And what is chlorine? Okay, so 6 minus 5 is 1. 1 minus 5 is 6, so 0.61. Okay, is that enough to be polar? The bonds are polar. Excuse me. Which means, which way should this arrow point? Towards chlorine. This one should go towards chlorine, right? This one here should go back towards chlorine. And this one here should come out towards chlorine. See my beautiful three-dimensional arrows? You don't need to worry about that. But there they are. Now, what do you think? We have 4 dipoles here. We have 4 polar bonds. But what do we know about them? Why do you think they're going to cancel each other?
Because they're all pulling from the same. It's like if you were playing well with a person, if you're all pulling with the same force, so like say, somebody has guns, somebody has rifles, you're either first going to scare them apart, or you're not going to make them go anywhere because they're all pulling.
Yeah. So here's the deal. Let's imagine this. Let's say that you, and you had decided to steal my banana. Now, let's be clear. You're not getting my banana without a fight. I don't know. It's an analogy. Now, let us further suppose, actually, banana's a bad idea because it's really soft and it'll break apart. Let's say you're trying to steal my car keys. All right, so you're there.
Okay.
So you're all trying to steal my car keys. I don't want you to steal my car keys. Now, let's imagine something else that's really hypothetical, which is that we're all equally strong. Now, that's ridiculous because I'm much stronger than all of you. But if that weren't true, in some imaginary world where I am not incredibly strong, let's imagine instead that we're all of equal strength. Now, let me ask you this. If I am pulling this way, and they all lined up there and pulled, and we all pull with equal strength, which way are the keys going?
No.
No. If you're all that side, and I'm here, I pull, so I have one person pulling this way, and 3 people pulling that way. Which way do they go? Yeah, but now let's imagine we do it a little differently. Let's imagine that we all line up so we're exactly 109.5 degrees away from each other. And I pull this way, you pull that way, and some poor sucker has to pull down that way, and then some really poor sucker has to hang from the ceiling and pull that way. So we're all exactly equal angles away from each other pulling. Now what happens?
Somebody comes in and kicks you in the knee.
Me in the knee? Nobody would be so foolish. They would fear my swift revenge. But no, do the keys move in that case where we're all at equal angles to each other? They can't, right? Because on net, that pull is canceled by all of the other pulls because the angles are all equal and because all the pulls are of equal strength. So in this case, even though we have 4 dipoles, do we have a net dipole? So all 4 cancel. No net dipole. And so is this polar or non-polar? Very good. So CCl4 is non-polar, even though all the bonds inside of it are polar, which is a little bit weird, right? That's the grade 12 understanding. You have to understand that even if the bonds are polar, it doesn't necessarily make the compound polar.
It kind of does make sense. We do it in TV for both we're all thanks to the same thing. It doesn't really go anywhere.
That's right. And I can show you this in 3 dimensions as well. So if we look here, CCl4. But first of all, does everyone see that tetrahedral shape?
Where's carbon?
In the middle.
No, like on the earlier.
As a rule of thumb in more advanced Lewis diagrams, carbon is never shown. Anytime there's an intersection of lines, we understand it to be a carbon. When we get to organics and you have chains that are like 22 carbons long, you'll appreciate that fact. And they don't bother drawing hydrogens at all. They're just assumed to be there. So if we look, again, we put the bond dipoles in here. There they are, all 4. But if I try to add an overall dipole, do we see one? Nothing, because they cancel each other perfectly. Does that kind of make sense? Now, on the other hand, if I put a hydrogen up here instead, what am I going to see now? Well, now, if we show the bond dipoles, we still have those same 3 big dipoles here, and then carbon and hydrogen have a very small, insignificant dipole. What am I going to see now? Yeah, all the left-right should still cancel out, right? But we should see a net dipole going down. Let's find out. Hopefully this doesn't screw me over. No, there it is. See? Does that make sense? So if they're symmetrical, they cancel. If they're not symmetrical, they don't cancel. So as soon as I changed one of the chlorines to a hydrogen, now I get a non-symmetrical arrangement of dipoles, and we get an overall dipole. So CCl3H would be, we would actually call that HCCl3, but whatever. HCCl3 would be considered polar. That make sense? Okay. By the way, molview.org, check your work. Can't recommend it enough. So I want to show a slightly different example here, actually, which is if I had, let's do like NF3. If I had, oh gosh, if I had nitrogen, fluorine, fluorine, and fluorine, nitrogen overall should have 5 electrons. Fluorine should have 7 each, for 21, for a total of 26. So I know I'm kind of rushing through this, but I just don't want to spend forever on the Lewis diagram. I'm going to fill the octets. That brings me to 8. The next one will bring me to 16. And the third one will bring me to 24. What do I need to do? Good. And now, do I need any double bonds or anything? No, everything's happy, right? Is everyone comfortable with that? I know I went quick. Did I go too quick? Don't be shy. Okay, now let's look. Okay, let's talk about nitrogen. What does it have? It's got how many sigma bonds? How many pi bonds? How many lone pairs? Okay. With that in mind, what's nitrogen's hybridization state? Very good. sp3, because the only thing that makes it lower than sp3 is if we have to save a p orbital. And we only save a p orbital for a pi bond. So since there's no pi bonds, got to be sp3, right? But this only has 3 things attached to it. What's its shape? Pyramid. Good. It's not trigonal planar, right? It's not the flat triangle. This would be, by the way, what would we expect this bond angle to be? It's based on 109.5, but it's got to be 107, 108. It's got to be a little lower because of what? The lone pair of electrons. Remember, lone pairs of electrons crowd the others out. So we would expect this to be maybe roughly 108 degrees. I mean, that's a guess, but we know it won't be as big as 109.5, and it certainly won't be 120, right? This is not sp2 hybridization. This is sp3 hybridization. This is a pyramid. Well, now, if it's a pyramid, which way does the dipole go here? Which has a higher electronegativity, nitrogen or fluorine? Yeah, can everyone see that? It's like 0.94 different. So here, we are going down to the fluorine, down to the fluorine, and down to the fluorine. These look like they cancel in 2 dimensions, right? But if you look at it in 3 dimensions, and this is why we have to be careful, if we really know that this thing kind of looks like this, where there's a fluorine up front on the side, one that comes to the front, one that comes to the back, and they all go kind of down, now we can see, and I actually wish I'd drawn that even more dramatically, like kind of. Does that make sense? Now, if we look at these dipoles, the left-right of it definitely is going to cancel out, right? Like the left and the right all cancel, but overall, all of those arrows point down. So we should end up with an overall dipole that goes straight down. And this is why we have to know whether this thing is a 3-dimensional shape or a 2-dimensional shape. We have to know if it's linear or bent. We have to know if it's trigonal planar or if it's pyramidal, because those have different outcomes. Does that make sense? Tomorrow I'm going to give you guys a quiz, not on the dipole stuff. The dipole stuff I will work on Friday, kind of quizzing you on, but I am going to quiz you tomorrow on your ability to draw Lewis structures. All right? And to talk about the hybridization state, and to talk about the 3D shape it is. I want you to be able to look at a Lewis diagram you've drawn and tell me, is the central atom SP, SP2, or SP3? Once I know that, what's the overall shape of this thing? All right, you need to be able to do that, so we're going to quiz on it tomorrow. I've given you lots of practice. I think we'll do the quiz on it tomorrow at the end of class, so we can spend the duration of class taking up questions, looking at stuff, and then at the end of class, in the last 10 minutes, we'll do a quiz. Does that make sense? Okay, I don't think there's any more examples on here, are there? Okay. If you, oh, I wanted to show you this one in the 3D model, just to show you that I'm not full of it. Full of it. So what was that? That was nitrogen trifluoride. All right, so there it is. And if we look, can everyone see that is not, yes, from the top, it looks as though it's just a triangle. But as soon as we start manipulating it in 3D, we see that it, in fact, has that kind of tripod orientation, which means where is the lone pair of electrons? Up top here, right? That's where the lone pair of electrons would be. If I go to add the individual dipoles, they run towards the fluorine. When I go to add the net dipole, what should I see? It should go straight down. And there it is. Everyone see that? I cannot tell you how much I wish this technology existed when I was learning this stuff in school. It's pretty, we used to like make them out of the wooden models, and that's all well and good for making the model, but then like we'd like try and like physically show the dipoles and like how they cancel, and it was not intuitive. You can, but this is helpful, so I encourage you again to use it. I'll throw a link to it up on Teams. In fact, maybe I'll do that right now. Molviewer.org. Now, if you look on this next page, I've just given you a boatload of questions. This questions 1 and 2 are just draw the Lewis diagram, tell me about shape. There's nothing about dipoles in this, all right? This is just boatloads of practice. Do you need to do every one? Maybe. I would say this, keep doing them until it just feels boring and easy. If you found the last one even a little bit confusing, you're not good enough yet. Do another one. All right, that's going to be different for every one of you. We all have different natural gifts. Different things are easy for some of us. Different things are tough. Somebody may do A and B of this and go, yeah, got it. That makes sense to me. I can identify the hybridization state. I can do that. Even then, don't do less than 4 or 5. All right. But some of you may have to go all the way up to P to get there. Note the charges, by the way. A few of these have charges at the end. Here we have for polyatomic ions, do the same. And then down here, draw the Lewis structure, and then talk to me about dipoles. When it says vectors, by the way, that's the actual physical arrow. I don't know if I use that word or not, but the actual, like, the dipole is the physical thing in real life, like the movement of electrons. The little arrow we draw is called a vector. And if you've taken physics, you know about vectors. Have you guys done vectors in physics? Yeah, so there you go. Cool. Does anyone have any questions about that? Okay, again, I will throw the reach ahead lessons up online. My advice would be to do them after test time. I wouldn't start stuffing my brain with extra knowledge before the unit test, right? I'd focus on what you need to know. But then when it's done and we're in the early stages of next unit, that's a good time to get that stuff done. But it's a pretty rich deal. I decided last night, talked to my wife. She gave me advice, as she often does. She said, make it worth some bonus marks. Don't be Scrooge. And I said, but I like being Scrooge. And she said, no, be nice. So I'm being nice. But definitely get through some of this practice, all right? It's important. Because we are on track for either Monday, Tuesday test. That comes fairly quickly. No new material after this. We've covered everything we're going to cover. We're just going to spend the next few days working to reinforce that. But let's make sure we do that. Yes? Monday or Tuesday. Yep. Oh, of course. Yes, yes, yes. Let me just shut this off.